Hey everyone, welcome to this explainer. We're diving into classical mechanics today, but honestly, in a way that might just completely change how you view the physical world around you. We so often look at physics as this giant, intimidating wall of complex math and abstract equations, right? But what if I told you it's actually much simpler than that? What if instead we treated the laws of physics not as some grueling math test, but as a highly intuitive, strictly regulated financial system? Okay, let's dive into this. Think about it. Did you know you participate in a massive, invisible economic system every time you take a single step? It's totally true. Every time you walk down the street, lift a cup of coffee, or, even just sit back in your chair, you are participating in a massive, invisible economy. The physical universe operates on incredibly strict rules of exchange and commerce. Nothing is free, nothing is wasted, and absolutely every single action requires a transaction. By the end of our lesson today, you're going to see exactly how this universal economy really works. So here is the roadmap for our step-by-step lesson today. First up, the economy of motion. Next, defining the transaction. Then, savings and spending, followed by the invisible taxes, the rate of exchange, and finally, crashing the system. Let's get to it. Starting off with Section 1, the economy of motion, where we'll look at energy as currency. Energy is the currency of the physical world. I really want you to keep that quote in the back of your mind throughout this entire explainer. Because just like money makes the human world go round, allowing us to buy goods, build cities, and trade across oceans, energy is the literal currency that allows the universe to actually do things. If you want to move an object, heat up a room, or light up a whole city, well, you have to pay for it. And the universe, it only accepts one form of payment: energy. Now, there are three main pillars to understand the architecture of motion. First, as we just established, energy is the currency. It's the physical cash. Second, work is the transaction. It's the actual process of moving that currency from one account to another. And third, power is the rate of exchange. It's how fast that transaction takes place. Once you grasp these three simple concepts, classical mechanics literally just becomes an exercise in basic accounting. Let's talk about our cash. In physics, kinetic energy is your cash in hand. It is the energy an object possesses strictly by virtue of being in active motion. A rolling bowling ball, it's got cash in hand. A speeding car, a whole lot of cash in hand. But here's the really fascinating part. Look at the kinetic energy equation. It equals 1/2 mass times velocity squared. Because that's speed, the velocity is squared. If you double your speed down the highway, you don't just double your kinetic energy, you actually quadruple it. Think about that the next time you hit the gas pedal. You are spending your physical currency at an exponential rate, which means your brakes are going to have to do 4 times the work to stop you. Moving right along to Section 2, defining the transaction or work in physics. In our human world, a transaction is swiping a credit card or handing over a dollar bill. In the physical world, that transaction is called work. Work is a mechanical transaction where effort, which in physics we call force, and displacement align to successfully transfer energy. So the absolute crucial point here is this. In physics, doing work literally means moving energy from one place or object to another. But here is where the universe plays a pretty funny trick on us. Let's say you go outside right now and push against a solid brick wall with all your might for 10 solid minutes. You're going to be exhausted, sweating, feeling like you just did a massive amount of work, right? But mechanically, the wall didn't move. The displacement is 0. In the economy of physics, effort without displacement yields exactly 0 work. You spent internal energy from your morning breakfast, sure, but you didn't transfer a single drop of it to the wall. Mechanically speaking, your transaction was flat out declined. And transactions can actually go a few different ways, depending entirely on how your effort aligns with the motion. Positive work is like making a deposit into an account. You push a box forward in the exact direction it's already moving, adding energy to it. Then there's zero work. If you hold a heavy barbell straight above your head and walk forward, your upward force is totally perpendicular to your forward motion, so 0 energy is transferred to the barbell's forward speed. And finally, negative work. This is a withdrawal. Think of friction acting against a sliding tire, aggressively draining energy out of the object and slowing it right down. Which brings us perfectly to the ultimate bank statement of classical mechanics, the work-energy theorem. It's actually beautiful in its simplicity. It tells us that the initial kinetic energy of an object plus the net work done on it perfectly equals its final kinetic energy. Work is the exact mechanism that changes an object's speed. If you want a static ball to start rolling, you absolutely must perform positive work on it. It flawlessly connects our mechanical transactions directly to our physical cash on hand. Now let's jump into Section 3, savings and spending. We're looking at potential versus kinetic energy. So, we know kinetic energy is our cash in hand. It's active, it's moving, it's doing things right now. But what if you aren't currently moving? Well, the physical economy also offers a savings account, and we call that potential energy. Potential energy is not active motion, it is stored position. It is simply the capacity to do work, safely tucked away for a rainy day. Let's use a simple daily analogy here. Picture a ball resting right on the very edge of a cliff. It has zero kinetic energy at this exact moment because it's completely still, but it is high up in a gravitational field. Simply by virtue of its physical position, it has a massive amount of potential energy. Gravity has effectively handed it an enormous savings account. It is pure energy just waiting to be unleashed. Now, what happens if somebody just nudges that ball off the ledge? Boom, rapid withdrawal. In step 1, at the very top, it's 100% in savings. In step 2, as it's falling, the universe is rapidly converting that stored potential energy into active kinetic cash. It's basically running to the ATM and pulling out cash as fast as it can. By step 3, the split second before it smashes into the ground at maximum speed, all of its potential energy is gone, completely converted into kinetic cash. And this highlights one of the absolutely most comforting rules of our physical economy, the conservation ledger. For conservative forces like gravity, the bank never, ever loses a penny. If you track the total mechanical energy from the top of the cliff all the way to the bottom, the total amount never changes. It is perfectly conserved. The universe didn't lose any money. It simply changed the currency type from potential savings to kinetic cash. The ledger remains perfectly balanced. All right, moving to Section 4, the invisible taxes. We'll be talking about friction and heat. Because let's be real, no economy operates perfectly without a few hidden fees, right? In the real world, if you slide a book across the table, it doesn't just glide forever. It stops. Why? Friction. Friction is what we call a non-conservative force. It acts as a permanent, non-refundable tax on our physical system. It does negative work, draining mechanical energy from our kinetic and potential accounts, and it transforms it into heat. Now, that energy isn't destroyed, remember, the universe cannot destroy energy, but it is permanently removed from our usable mechanical ledger. It is just the literal cost of doing business in a physical universe. And sometimes the cost of doing business fluctuates. In a perfect theoretical textbook, you push an object with a constant, unyielding force. But in reality, your effort changes. You push hard, then you get a bit tired, then you push hard again. If you see a graph of variable forces, don't let it intimidate you. When the exchange rate of your force fluctuates over time, we just use a bit of calculus to find the exact area under the curve. That area is simply adding up all those tiny, changing individual transactions to find the total overall work done. Think of it as just a highly detailed, itemized receipt. Let's look at Section 5, the rate of exchange, where we calculate power. So we know how to transfer energy, but in the real world, we really care about how fast we can do it. If work is the total energy transferred, power is simply how fast that transfer happens. It's work divided by time. Think about an elevator. Moving an elevator car full of people from the ground floor to the 10th floor requires a specific fixed amount of work. That transaction cost is set in stone. But the elevator motor's power determines if that transaction takes 10 seconds or 10 minutes. Power is basically the processing speed of the bank. We measure this in watts, which is simply 1 joule of energy processed per second. Finally, Section 6, crashing the system. Let's look at the physics of collisions. What happens when things go wrong and two separate economies violently collide? We use a collision diagnostic matrix. When two objects hit each other, total momentum is always conserved. That's a hard, unbreakable rule. Momentum dictates the physical direction the twisted metal is going to slide after the crash. But what about kinetic energy? In a purely elastic collision, like two billiard balls cleanly clicking together, the kinetic energy is perfectly conserved. They bounce off each other flawlessly. But in real life, like a car crash, we have inelastic collisions. Kinetic energy is permanently lost. It's spent on brutally crushing the metal, generating heat, and making a terrifyingly loud sound. So the key takeaway here, momentum dictates the direction of the crash, but the loss of kinetic energy tells us about the survivability of the impact. The more energy lost to deformation, the more violent the crash. And that brings us to the end of our explainer. We've seen today that the physical world around us is bound by a strict, fascinating economy. Energy is the currency, work is the transaction, and every single movement is a highly calculated exchange. So I'll leave you with this final, provocative thought. In a universe where energy is never truly created or destroyed, but merely traded from one account to another, what are you doing with your currency? Next time you walk up a flight of stairs or accidentally drop your keys, I really hope you see the incredible, invisible ledger balancing itself out right in front of your eyes. Thank you so much for joining me today, and keep questioning the world around you.